Step straight into the memory palace of a Cambridge exam hall. The air is heavy, the invigilator is pacing the aisles. Every single tick of that giant clock on the wall echoes right in your ears, and your final grade is completely on the line. The paper sitting on that wobbly desk in front of you is demanding absolute precision, and you are literally seconds away from a make or break moment. You've spent months preparing for this exact day, but right now, it all boils down to how you perform under this intense, pressurized microscope. Imagine this absolute nightmare scenario. You hit the final page. You are staring down a brutally complex crane and pivot problem. You glance up. 5 minutes left. 5 critical marks on the line. You can literally feel the physical pressure of losing those specific marks, knowing they could easily be the razor-thin difference between a B and an A star. So what's your next move? Do you just freeze up, hoping the right numbers magically jump off the page? Or do you deploy a systematic, battle-tested strategy to ruthlessly secure every single one of those marks before the examiner says pens down? Notice the setup of what we're going to call the crane trap. We've got a 10,000 Newton concrete balancing weight, a massive 30-meter jib, and a very crucial, very specific pivot planted right in the middle. Most students, when they get hit with this under extreme time pressure, immediately panic. They just start grabbing numbers and multiplying them together, hoping for the best. They take the 10,000 newtons and just arbitrarily smash it against the 30 or the 25. They completely ignore the pivot's specific distances. They treat a complex moments question like a simple times table, totally abandoning the actual physics of equilibrium. In this painful comparison right here, this is exactly why ordinary rote revision completely fails you in the real exam. Knowing the basic math just isn't enough if you don't understand the examiner's specific command words and their carefully laid traps. That flawed student answer on the left just mashes given values together on a wing and a prayer. But look at the examiner's mark scheme. It strictly, absolutely requires you to identify that pivot as the absolute center of rotation. You have to calculate the moment using the exact perpendicular distance of 5 meters from that pivot to the 10,000 Newton weight. Do anything less, and you score a flat 0. To stop bleeding marks on these high-stakes questions, we are going to use a 4-part top-band framework to reverse engineer exactly what the Cambridge mark scheme demands from you. Step 1 is identifying the core concept, like recognizing immediately that you're dealing with a moments question, not a basic forces calculation. Step 2 is pulling the evidence or data straight from the scenario. Step 3 is applying strict scientific reasoning to bind that data to the concept. And Step 4 is matching the exact examiner wording expected in the 0625 syllabus. This is how top-tier students construct their answers. They aren't guessing. They are building a mathematically airtight argument. Now, just like ignoring the pivot completely ruins a moment's calculation, there is a hidden examiner clue that changes your momentum calculations entirely. It is, without a doubt, the single biggest trap in the entire syllabus, and thousands of students fall for it every year. In just a moment, I'll show you exactly what this hidden clue is so you never miss it. But first, you have to understand the underlying physics framework that makes this exact clue incredibly obvious to a trained eye. So let's build that foundation together right now. Let's execute our framework's first step, the concept, by clearly defining a vector. A vector is a variable that has both a magnitude, which just means size, and a very specific direction. Now, here is the crucial point you have to internalize. Direction is not just some optional, nice-to-have detail. It is fundamentally baked into the physical reality of the variable. If you ignore direction, your math will flat out lie to you. It's literally the difference between stepping forward into an elevator and stepping forward into an empty elevator shaft. Direction is absolutely everything. Which leads us straight into momentum. Momentum is defined as the product of mass and velocity. You know the equation, P equals m times v. But here is the kicker. Because velocity is a vector, momentum has to be a vector too. It inherits that directional property. This means that if you're looking at motion in a straight line, one direction has to be mathematically positive, and the completely opposite direction must be mathematically negative. Getting this positive-negative dichotomy locked down is the absolute bedrock of scoring top marks in any collision question Cambridge throws at you. Check out the before and after states of the collision here. This perfectly establishes the physical evidence step from our framework. I want you to take a really close look at the distinct arrows for Object 1 and Object 2. Before the collision, they are moving at initial velocities, u1 and u2. After the impact, they move at final velocities, v1 and v2. You need to realize right now that those arrows aren't just decorative little graphics to make the exam page look pretty. They are literal, strict mathematical instructions telling you exactly what positive or negative signs to use in your calculation. And this perfectly visualizes the cornerstone of the whole topic, the law of conservation of momentum. It states that the total momentum before an event is exactly equal to the total momentum after the event. That is, assuming no external forces like friction or air resistance are messing with the system. Think of it like a cosmic accounting trick. No momentum is ever truly lost. It is only ever transferred from one object to another. This exact principle is the scientific reasoning step you must actively deploy in your written exam to lock down those massive method marks. Let's see how all of this builds out your ultimate formula toolkit. These three equations are your absolute arsenal for providing data-driven evidence. You've got your basic momentum equation for single objects, you've got your long-form conservation equation for complex, multi-object collisions, and you've got your impulse equation for crashes and impacts. Memorizing this specific set is non-negotiable. Knowing exactly when to reach in and pull the right specific tool from this kit is exactly what separates average candidates from the top-tier A-star performers. Notice how impulse, elegantly represented by the equation force times time equals mv minus mu, perfectly bridges the gap between force, time, and the change in momentum. You can think of impulse in two ways, either as the force multiplied by the duration it acts, or simply as the total change in momentum itself. And listen, here is where examiners love to trick students. The exam will test you on both definitions, sometimes in the exact same multi-part question, specifically trying to see if you actually realize that force times time is the exact same thing as a change in momentum. All right, here is the critical distinction and that major hidden clue I promised you earlier. The negative sign dictates direction, and dropping it is the absolute #1 reason students hemorrhage marks on collision calculations. An ordinary answer carelessly writes down 10 kilogram-meters per second, walking blindly right into the trap. The top-end answer correctly identifies the rebound or the opposite direction of travel and purposefully writes -10. Let me be clear, that one single little dash is literally worth an entire grade boundary. Okay, time for an interactive challenge to test if you've really got this locked in. I want you to pause and predict the outcome of this practical scenario using the exact vector rules we've just established. Imagine a trolley explosion where two connected laboratory carts are suddenly triggered and pushed apart by a compressed spring. What fundamentally has to happen to the mathematical momentum values if they shoot off in completely opposite directions? Take a second, lock in your answer right now before we move on. And here comes the examiner's red pen correction. Did you catch it? Velocity values in the opposite direction absolutely must be negative. If you didn't assign a negative value to the trolley moving backward, you just fell headfirst into the classic examiner trap we've been warning you about. Your total momentum after the explosion would be completely wrong because you simply added two positive numbers together instead of letting them correctly sum to 0 exactly as the conservation law demands. To fulfill the final step of our framework, the examiner wording, always run your completed answer through this final mental checklist. It ensures you haven't made any painful formatting mistakes right at the finish line. Did you include the correct units? Did you round too early? Listen, compounding rounding errors throughout a multi-step calculation will absolutely ruin your final value and cost you the accuracy mark. Are your written explanations hyperspecific or are they vague? And is your conclusion firmly backed by the data you just painstakingly calculated? You now possess the deep physics framework to secure top marks on forces, momentum, and impulse. You know exactly how to dodge the traps that catch out thousands of other students. But there is one final, completely unresolved problem you must overcome to survive that ticking exam clock we talked about at the very start. You have the knowledge in your head right now, but the final room remains locked until you can actually execute it perfectly on paper under severe, unforgiving time pressure. To unlock that final room and totally master the timed answer writing system, you must take the mandatory next step. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. Seriously, don't leave your final grade to chance. Get in there, apply the framework, and I'll see you in the next explainer. But before you go, ask yourself this one provocative question. If momentum is always perfectly conserved in a collision, where exactly does the kinetic energy go when two fast-moving cars crash and come to a dead, crumpled stop? Think about it.